So last lecture we had looked at finding out the position of center of mass for discrete particle system using the general formula in vector form for position vector. Then we also looked at a couple of examples of usage of integration of finding the center of mass of a system of particles which is continuous in mass distribution using definite integration by taking differential elements dm and then integrating instead of the summation we use the integration. So let's continue from that point onwards today. Okay, so the last thing we had left off at was the calculation of center of mass for a continuous mass distribution. Okay, by application of integration. So we had seen that in general, if we have any sort of continuous mass distribution like this, and with respect to some coordinate frame like this, you want to find the position vector of the center of mass, or we want to find the individual xyz coordinates of the center of mass. Then what we have to do is we have to break this into differential elements, and for each differential element we should find some way of expressing the position vector r. And then just like for a discrete mass system, we define the position vector of the center of mass as summation m into r divided by summation m. For a continuous mass system, we replace the summation with integration. So it becomes integration r dm divided by integration dm, or integration r dm divided by m, which is the total mass. Okay. So we had seen one example of this with a linear distribution of mass with variable density and all that. So we will continue from that point today. But first of all, we will organize this application of integration systematically according to our type of system. Okay. So we will see that depending on how the mass distribution is occurring for the continuous mass distribution, we can classify it into three categories. So continuous mass distribution systems. Okay, they can have these following three categories. They can be linear distributions. They can be surfaces or surface distributions. Okay, or they can be volume distributions. And accordingly, we have to learn how to choose our differential element and how to set up the integration. So a linear distribution, for example, would be a thin rod or a thin arc, okay, or a rope, chain, etc. The mass is distributed over a length distribution or a linear distribution. Similarly, a surface distribution would be any surface type of material. So it could be a laminar surface like a rectangular plate or thin disc, okay. Or it could even be a non-laminar surface. For example, it could be a thin spherical shell, not a solid sphere, but a spherical shell, okay. Or a hollow conical shell. So these are all examples where mass is distributed over a surface, and volume distributions are very easy to understand. Any three-dimensional solid rigid body. Okay. Example, a solid sphere or cuboid or cone or cylinder, or any such thing. Okay. So to be able to apply the integration method properly to calculate the position of center of mass for a continuous mass distribution system, we have to be able to first of all classify our mass distribution into one of these three categories, so that we know how to further apply this integration formula that we've written about. So just make a note of this quickly. Okay.
Sir,
Yes.
sir, for that in that linear distribution, did you write thin arc up below that thin rod?
Yes, thin arc. Like, if you take a metallic rod, like there's a straight metallic rod, and then bend it into an arc shape, then that is what we mean by saying a thin arc. It might be
Got it.
semicircular, it might be a full circle, it might be just subtending some angle. So this is an example of an arc. What happened? Okay. Okay, so we'll come back to each of these and we'll understand further. Now, in the case of linear distribution, what we do is the dm element that we take. Okay, so dm is our differential mass element. That means a small fraction of the mass of the whole body. So this dm mass element becomes of the type lambda dl, where lambda is linear mass density, like we had done for the previous question that day. It's a linear mass density, or it's a term which is mass per unit length. Okay, and dl is a differential length. That means it's a very small length. So for example, the rod, we will cut it into differential lengths like this. The arc, we will cut it into differential sections of length dl each. So that section is of mass dm, where dm is equal to lambda times dl, where lambda has the meaning of linear mass density or mass per unit length, and dl is a very small length. But similarly, in the case of surface, we have to express dm as a different type of element. dm will become mass per unit area into a small area. So here sigma is surface mass density. So it is mass per unit area. Okay. And dA is a differential surface element. So it's a small area. It's a differential area. So for example, this is some kind of a surface I have, like a crumpled piece of paper. So this is some kind of a surface. So my differential area will be a small section of that. So this will be my differential area. Okay. So this becomes how we select our differential element of mass in case of the mass distribution being a surface distribution. So accordingly, the mass element also has to be a surface element. It has to be of the type sigma into dA, where sigma has dimension of mass per unit area and dA has the dimension of a differential area, or dA is a very small area, whereas dl was a very small length. Okay. And like that, if we talk about volume distribution now, for volume distribution, dm directly becomes density into a very small volume. So rho is, properly we say it is volume density, or it is volume per unit, I mean mass per unit volume. So it is a common meaning of the term density, mass per unit volume. But similarly, dV is a differential volume element. So for example, we have some kind of an arbitrary shaped three-dimensional material like this. Okay. So a small section of its volume that has to become a volume element. So whenever we are using integration to find the position of the center of mass, so the first step we have to understand is that when we are using integration for RCM is equal to R dm integration. So what is the dm? In case it's a linear distribution, it's of the type lambda dl. In case it's a surface distribution, it's of the type sigma dA. And in case it's a volume distribution, it's of the type density into volume, or rho into dV. And these are the standard symbols we use. Lambda for linear mass density, sigma for surface density, and rho for volume density. So these concepts that we are discussing in integration here, and we are developing these techniques, they are going to be useful not only in this chapter for center of mass, but in a lot of future chapters also. Chapters like rotational mechanics, gravitation, electrostatics, various other chapters where we'll be using the similar kind of techniques for application of integration.
Sir,
Yes.
sir, could you just repeat what you said?
Which part, Beta?
Sir, that usage in the future chapters, that one you just said now.
In future chapters, we'll be using the same kind of techniques in integration, Beta, like we are doing over here. So these techniques we're developing, they are going to be important not only for this chapter, but in future chapters also, like electrostatics, gravitation, rotational mechanics, etc. So as we go from chapter to chapter, you will see that.
Sir, you mean integration?
Yes, the techniques of integration. Okay, so the first step in integration is whenever we are integrating over a distribution, it is to be able to understand whether the distribution is linear, surface, or volume. So accordingly, the differential element is a length element dl type, or a surface element of the type dA, or a volume element of the type dV. So even this first step that we are writing of classification of different distributions, this is useful in integration in general, not just in this chapter, but in the application of integration in general. So you will experience that as we go from chapter to chapter. I'm just telling you the importance of this thing here is not just for this chapter. It will be important in future chapters also. Okay, so let's start with examples of linear distributions. So one example we had already seen last time, the thin rod, that kind of thing,
Yes,
which
sir.
had non-uniform linear mass density. So let's move on with more examples.
Sir, could you just scroll up?
Okay, I'll go back just a moment.
Done, sir.
Okay. So let's take some examples of linear distributions to understand this better now. So now one very interesting example of a linear distribution we'll see is if we have a thin rod which we have bent into the shape of a semicircular arc, not a circular arc but a semicircular arc. So just a minute, I'll draw the whole shape, then we'll understand. So these are just two imaginary guidelines. So what we have over here, as you can see, is a thin uniform wire or rod bent into a semicircular arc. Okay, which has mass m, total mass, and radius of curvature capital R. So that's this R over here. Okay, and the center of curvature, not the center of mass, but the center of curvature is the origin of the coordinate system. So you can see that the y-axis bisects it symmetrically. Okay, you can see that total 180-degree angle is bisected by the y-axis over here. So y-axis is an axis of symmetry. So once we process this information that the mass distribution is uniform, because it's a uniform thin wire or rod or whatever, we understand that the axis of symmetry is such that the center of mass will lie on the y-axis. The center of mass lies on the y-axis because it is an axis of symmetry. It's a symmetry axis of the system. The left side is a mirror image of the right side in terms of mass distribution. So that tells me that it has to lie on the y-axis at some point, let's say C, which is given by 0, y coordinate of the center of mass. So this is somewhere where my center of mass should logically lie. Okay. So now the question is, how do I find the y coordinate of the center of mass? So I have to use this equation. YCM is integration of y dm divided by total mass. Okay. This formula is directly coming from the general formula that position vector of center of mass is integration r dm divided by total mass, which means that x coordinate is integration x dm, y coordinate is integration y dm, and z coordinate is integration z dm by total mass. So here we know that the center of mass lies on the y-axis. We know the x coordinate is already 0, and the whole shape is itself in the xy plane. So there's no question of any z coordinate. The center of mass is lying directly on the y coordinate, so the z coordinate is also 0. So we just have to find the y coordinate of the center of mass, YCM, we have to find. So how do we find this? So to find this, now we have to make use of this, where further we find that dm is a lambda dl type of element. It's a linear element. Why? Because the bent rod is a linear distribution of mass. It's not a surface, or it is not a three-dimensional volume, but mass is distributed over a certain length. This is like the perimeter of the semicircle.
Sir,
Yes.
sir, but how we know that
Yes,
center
Bhattacharya.
of mass lies on y-axis?
How we know that? Na? See, it is like you can understand na, that the mass per unit length is uniform for the thin wire, right? And you can see the y-axis is drawn in such a way that it is bisecting it into two equal quarter circles, no, on either side. So the distribution of mass is symmetric on either side of the y-axis.
Yes, sir.
Understood now? So that's how we recognize that it's a symmetry axis.
Okay, sir.
So that is coming from our geometrical knowledge actually. That basically, see what's happening. The semicircle is subtending how much angle at the center of curvature. It's subtending a total angle of 180 degrees. So the axis which is cutting this angle into two equal halves of 90 and 90, that has to be a symmetry axis. So that's why we know that this is the symmetry axis. Because half the mass is on this side, half the mass is on this side, and the distribution of mass is equal. Now, these two particles, this pair of particles are always symmetrically placed. This one and this one, this one and this one, like this. So all the particles on this side are symmetrically placed with respect to all the particles on this side. So we know that the y-axis is
Yes,
an
sir.
axis of symmetry. Okay. So that is something also that we have to learn to do when we see any kind of geometrical shape. If our knowledge of geometry is telling us that okay, we know some axis of symmetry, then it makes life easier because we have to calculate only one coordinate then. And for example, if I knew two axes of symmetry, then I would not have to use integration because obviously wherever they would intersect, that would give me the position of the center of mass. Okay. So if I, for example, forget about this question for a moment. If I had some kind of an arbitrary shape like this, and I knew by some method that this is one axis of symmetry, and I knew that this is another axis of symmetry, then I would be sure that the center of mass is here because both the axes of symmetry can only coincide at one point or intersect at one point, which is the center of mass.
Yes.
No, which is why if we had the circular arc, we know that the center of mass is at the geometrical center because any diameter is a symmetry axis and all the diameters, they are intersecting at the common center of curvature. So that becomes, so we don't need to do integration. But here we don't unfortunately directly know the second axis of symmetry. So we have to use integration to find the YC. Okay, now this point is clear, beta?
Yes, sir.
Okay. Now I'll tell you later that at the laboratory level, there's a very easy way to trace the axis of symmetry for any given body, especially if it is laminar in shape. But currently, let's look at how we will use integration next over here. Okay. So next thing is we are seeing that in the application of this formula, we have to replace dm with this. Okay. So in this, what is lambda going to be next? Lambda is going to be mass per unit length. So this was basically a uniform distribution of mass m over the total length of the semicircle, which is pi r. So I have to replace lambda with the mass of the semi-ring divided by the circumference of it, which is pi r. Because it's a semi-ring, so the circumference is only pi r. Okay. And the other thing is, now I will use one of the principles that we will take as a sort of rule in geometrical integrations. That is, that whenever we are integrating over a circular arc, we should express the length in terms of angle. Let me explain that point again. Okay, just give me a moment. So basically, whenever we are dealing with a situation where we want to identify a differential length element on a circular arc, it may be semicircular, it might be fully circular, it might not even be semicircular, it might just be some arbitrary angle, it doesn't matter. But on any circular shape, we identify a differential length like this. This is some differential length dl. So first of all, we identified the position of it by angular position. Okay. And secondly, that small element dl is basically a small arc. So that dl itself is subtending a small angle. Okay. So this itself is subtending a small angle d theta. So dl, which is our differential length element, okay, in this case it is a differential arc. Okay, so it subtends angle d theta. So we have the concept that angle is the ratio of arc upon radius. So theta in general is L by r, where L is the arc length. If L is an arc length, then the angle subtended by that arc at the center is given by this. So therefore, we have the relation that d theta is equal to dl by r, or we should write the length element dl in terms of angle as r d theta. So this. Okay. So now these two will be our next substitutions. Okay. First level of substitution, what I should replace dm with? I should replace it with lambda dm. Now second, over here, how much is the value of lambda? It should be m upon pi r. But then what is the value of dl? It should be replaced with r d theta, because as per this diagram, any section of the semicircle is a small arc itself dl, and that small arc is subtending a angle d theta. So its length dl can be expressed in terms of that very small angle d theta. Okay. So this is the method we have to use when we are integrating over the length of a circular arc. This statement that we have written, that a differential length element is equivalent to a differential arc. So this is the general concept when integrating over a circular arc. Okay, so whether it is in this chapter or in any future chapter, whenever dl is a differential arc length, we will express it as r d theta. Okay, so just make a note of this.
So
Okay,
now
so
we'll
now you can see,
integrate.
but there's still one thing. We still have to substitute y. So what we'll substitute as y over here? We have seen that in the integration that we have to use. Now next thing, we have to find the y coordinate by integrating y dm divided by total mass. So we have seen that dm will be replaced with lambda dl, where lambda further was m by pi r and dl was r d theta. So that is done. But what about y? What should we substitute y as? So y is nothing but the y coordinate of that differential particle. So in the diagram, you can see now what is the y coordinate of the differential particle. This is my differential element here, na, this one. So ये वाला जो differential elemental mass है dm, this is my particle. So what is its y coordinate? Its y coordinate is nothing but this one. Its y coordinate is this. The diagram, can you see that the y coordinate is r sine theta? Is it clear? Why it is r
Yes,
sine
sir.
theta?
Yes.
No, because see, on a circle, when we take any point like this at an angle theta like this, if its coordinates are x comma y, you can see that if the radius is r, the x coordinate is r cos theta, like we did in circular motion, and the y coordinate is r sine theta. So we should substitute y as r sine theta. Now you can see everything that we are substituting in the integration is going to be in terms of theta. So we will be able to complete the integration. Okay, and we have to complete this integration for all the particles lying at this point. So let's call this point A, right up to this point. So let's call this B. So from A to B, so A के लिए मेरा theta कितना होगा? It will be 0. Whereas by the time I reach the point B over here, my theta has become how much? It's become 180 degrees. So that will become the limit of the integration. So I will replace y with r sine theta. I will replace dm with m upon pi r into r d theta. Out of that, r will also cancel out. But my limits of integration at the point A, my lower limit of theta should be 0. And at the point B, my upper limit of theta should be pi or 180 degrees. And of course, don't forget there was a 1 by m outside. So take all the constants outside. So you'll see m upon pi comes outside. One of the r's cancels out. Sine theta d theta, and in the denominator I have m, so this will also cancel out, and this is going from theta equal to 0 to theta equal to pi. So it is becoming r by pi into sine theta d theta integrated from the lower limit theta equal to 0 to the upper limit theta equal to pi. And next step we will complete the integration by first doing the indefinite integration and then substituting the limits. So that will give me what? It will give me the y coordinate of the center of mass. Okay, so this process will seem a little bit lengthy and complicated in the beginning, but with practice, we will get used to this kind of application of integration. Okay, so anyone completed the integration? Now I'll just put aside the integration on this side. Sine theta indefinite integration is minus cos theta plus c. So when we put sine theta integration from alpha to beta, it becomes minus cos beta minus cos alpha. So it becomes cos alpha minus cos beta. Okay, so that's how this will go. So next step, this r by pi remains outside and minus cos theta. On this we have to put the limits 0 to pi. So that will become r by pi cos 0 minus cos pi. So that will become r by pi 1 minus of minus 1. So 2r by pi. Okay, so that becomes the y coordinate of the center of mass. So I'll explain the significance of this in a moment. So we can see that this is basically 2 upon 3.14 times r, or further approximately we can write that as about 0.64 times r. So you can see it's a little bit above the midpoint of the symmetry axis. Okay. So coming back to this shape, this was my semicircular arc. So if this was the symmetry axis, I've taken this as the origin. So this distance over here from the origin to the center of mass, this distance is 2r by pi, or approximately 0.64 times the radius. So in a sense, we can say that the mass of the semi-ring, it acts through that point C. The effective point through which the mass acts, which is the symmetry point or the center of mass, is that particular point C that we've labeled in the diagram.
So radius is not given, no?
The radius is according to the size of the ring. Na? So if I say it's a ring of 10-meter radius, then accordingly the answer will become 6.4 meters, or if it's 10 centimeters or it's 5 centimeters accordingly. But the standard formula is in terms of the radius. What?
Sir.
Yes.
Yes.
So, sir, overall, to find out the center of mass, you have used both that midpoint as well as that integration formula, is it?
Midpoint nahi beta, we have used the symmetry axis.
Okay, sir.
First thing we figured out that the center of mass is lying on the y-axis, so we don't need to find the x coordinate. We just need to find the y coordinate. Suppose we are not sure that it's lying on the y-axis, then we would have first have to calculate the x coordinate using that integration for x. xcm is integration x dm divided by total mass, and then repeat the integration but for y coordinate, and that's how we would have found the x and y coordinate. But here, fortunately for us, we know one symmetry axis, and that is the y-axis, so we did not need to calculate the x coordinate. The x coordinate was 0.
So that is 0 because this arc is already symmetry to the y-axis. Is that correct?
Yes, because we have already identified that it's a symmetry axis. Hai na?
That is why the center of mass for that x component should be at 0 for its symmetry nature.
Yes. So actually, if you use the formula for x coordinate of center of mass, you'll see you'll get it as 0. So it'll just prove the point that yes, it is a symmetry axis. If we just use this formula, na, तो अभी यहाँ पे देखो क्या करेंगे? The only difference is rest everything is the same, but instead of
Only
r
x
sine
coordinate.
theta, we'll have to substitute r cos theta. So everything else will remain the same, but this will become r cos theta into m by pi d theta divided by m. So we'll be left with this kind of integration: r by pi cos theta d theta integrated from theta equal to 0 to theta equal to pi. So this will become r by pi. Now antiderivative of cos is sine. So this you can see will give us 0 because sine pi is also 0. So this proves the point that, okay, but it's a very lengthy way of proving a very simple point that because it's on the symmetry axis, it's anyway obvious that x coordinate of center of mass should have been 0.
Got it, sir.
Okay. Okay, good. Okay. Now through this formula, na, yeah.
So,
Sorry?
sir, had this been symmetry to the x-axis, then its y component, some center of mass would be 0.
Yes, वैसा हो जाता. मतलब suppose मैंने ऐसा कुछ ले लिया है that my semi ring is placed like this. Now it's placed like this. Okay. Then this time, if I take this as my y-axis, and if I take this as my x-axis, okay, then my center of mass will be lying here, and this will be at xcm, comma 0. But again, we will get this time xcm as 2r by pi, so long as the mass distribution is uniform. You know? So
Okay,
this would
sir.
be this kind of case. Okay, but now we'll generalize this more and we'll make it like this: that suppose we have a thin uniform wire or rod bent into an arc, not necessarily a semi arc. So it is subtending any general angle. Alpha. Okay. So for example, if alpha is 2 pi, then it's a circle. It's a full circular arc. If alpha is equal to pi, it's a semicircular arc, the one we just saw. But it could be any arbitrary value also. So how to find the position of the center of mass of this? So it's the same technique, but with a bit of modification we have to do now. So that modification is how, let's understand. So now let us say this is our center of curvature here. Okay. But our semi arc, our arc is something very arbitrary now. It's like this, let's say. So it's more than 90 but less than 180 or something like this. Okay. Then where is the center of mass going to lie? So what we are going to have to understand is that first step, we will have to understand how much angle it is subtending. So the end points will have to be joined with the center of curvature. And then the angle between these two imaginary lines, that is the angle alpha we are talking about. So this angle here, from here to here, this angle, this is alpha. So once you got this, now we'll have to identify the symmetry line. So which is going to be the symmetry line, the one that bisects this angle. So that is, let's say, roughly speaking, this one. And we can take the perpendicular to this as our other axis. So we will just assign our x and y axis accordingly now, because it's more convenient to take the bisector as our y axis or our x axis. We'll take this as our y axis, this is our x axis. So this angle is equal to this angle is equal to alpha by 2. Okay. So again, the y axis we are arbitrarily taking as a symmetry axis. Okay. So it is the axis bisecting the alpha angle through O, which is the center of curvature. Okay. So this time we know that the center of mass will lie somewhere over here again. So center of mass will be at the point C, so 0, YCM, where YCM, how we will find? Again the same method. But the only difference is my limits will be different when I set up the integration. So this is how we'll proceed now. Okay. So just make a quick note or understanding of this part, then we'll set up the whole integration.
Here that diagram will be given. Okay.
Yeah, I mean diagram ऐसा दिया होगा कि suppose it's something like this, that
Yes, sir. Means x and y axis will be not given. Only
just
that
you will have to select the x and y axis yourself. Okay, for example, it's something like this is given, that there is some arc like this, okay, which is, let's say, subtending at the center of curvature. It's subtending an angle of, let's say, 120 degrees. This is the center of curvature and the angle is 120 degrees. So this is mass m and radius r. Now we have to find the position of the center of mass. Okay. So we'll have to convert that diagram to this first of all. So we'll have to identify our symmetry axis. That is the one which will be breaking this 120 into 60 and 60. And we'll say, okay, the center of mass lies somewhere on this axis now. Now, where on this axis with respect to the point O? For that, we have to develop the formula. Just like for the above one, the formula was 2r by pi. So here it will be some formula based on the general angle alpha, where in this case, the angle alpha is 120 degrees, or in SI units, it is 2 pi by 3 radians. So this would be an example of the application of this concept that we're just going to discuss. This would be the example. Okay. So now try to set up the integration yourself. I'll put it up in a moment. Okay, just try to set up the integration. If you like, you can draw a new diagram with the XY axis looking vertical and horizontal. Just reorient your arc in such a way that it's symmetrical about your vertical Y axis.
So radius is r, no?
Radius is capital R. So it will come as a formula in terms of capital R. But only that formula will have alpha somewhere involved in it. Okay. So let us set up the integration first. If you have already done it, just continue with the integration part. So now, as I just said, I'll just make the diagram little easier to understand, as if we have just turned our head in such a way that we are seeing the y-axis vertical now instead of seeing it diagonally like that. So I'm just reorienting my diagram like this. So imagine I'm seeing the y-axis vertical, okay, from that diagram. Oops. So this is my symmetry axis, and this is where my origin was lying. So this angle is alpha by 2, and this angle is alpha by 2. Okay. So now again what I will do is I will take at an arbitrary theta like this. I'll slice a small element so that dl will become r d theta. Okay. And this angle from here to here is theta, whereas this small angle is d theta. So this differential element again has a y coordinate, which is this one. And we will integrate finally from this point A to this point B. So we can see that dm, which is lambda dl. Okay. Now the thing is, if this radius is r, what is the total length of the rod? The length of the rod is going to be r alpha.
Yes, sir.
Because L is arc length. Okay. So angle is arc upon radius. Okay. So therefore lambda will be how much? Mass upon the total length. So that will be r alpha. Like this. So lambda becomes m upon r alpha, whereas dl as usual is r d theta. Okay, so I'll replace this with m by alpha into d theta. Okay. So dm is this, whereas the y coordinate of that point is as usual r sine theta in the diagram you can see. But also at the point A, you can see what is the value of theta. So that is a little bit complicated. It is 90 minus alpha by 2. Because this angle with the y-axis is alpha by 2. So this angle here, theta, at the point A, the angle with the x-axis, that angle theta is how much? It's 90 minus alpha by 2. And at B, the value of theta will become similarly 90 plus alpha by 2. Okay. So now that I have done this, I am ready to do the integration. The y coordinate of the center of mass is integration y dm divided by total mass from A to B. So I'll replace y with r sine theta. Okay. Slight difference, this is becoming m upon alpha instead of m by pi into d theta. Okay. And at A, theta's value is 90 minus alpha by 2. And at B, theta's value is 90 plus alpha by 2. Okay. So this divided by the total mass. So bring the constants outside. So mr by alpha integration of sine theta d theta from 90 minus alpha by 2 to 90 plus alpha by 2 divided by m. So again the m cancels out and we are left with r by alpha. Integration of sine theta is minus cos theta, but from theta equal to 90 minus alpha by 2 to theta equal to 90 plus alpha by 2. Again a bit of trigonometry will come in. cos of 90 minus x is sin x. Okay, whereas cos of 90 plus x is minus sin x. So you'll have to make use of this. So this will become r upon alpha into minus cos of 90 plus alpha by 2. Okay. Minus of minus, so that will become plus cos of 90 minus alpha by 2. So further, so become minus of minus sin alpha by 2 plus sin alpha by 2. So it becomes r into 2 sin alpha by 2. Okay. So the convenient way to remember this formula is that it is r into sin alpha by 2 divided by alpha by 2. And this is one of the formulae you'll have to remember directly, because this derivation is too lengthy to do in a question directly. So you have to memorize this formula. I'll give you a shortcut trick to remember this formula also. Okay, so once again, if this is our semi arc, I mean this is our arc, some arbitrary angle, and this is where the center of curvature is. This is where the center of mass is. Okay. So this angle is alpha by 2. This angle is alpha by 2. Then that distance OC, that is equal to YC, which is this much. Okay. Okay, so what we can also understand from this is that the semicircular arc is a special case of this.
Sir,
Yes.
Sir, can you explain that how you get the last step after second last step?
After this,
Yes, sir.
I mean this step to this step,
No, sir.
this to
Second last.
this one.
Yes, sir.
Okay. यहाँ पे ये 2 सिर्फ बाहर आ गया ना. So this is 2r by alpha sin alpha by 2 ना. So now you bring this 2 in the denominator, so it becomes this. Got it now?
Okay.
So it's pretty simple. Okay. Just take this down just a minute. I'll be back. Okay, people. So let's get back to this. What I was saying, that you can think of the semicircular arc formula that we just developed is a special case of this, general formula. Okay, that you put alpha as pi or 180 degrees. So you can see that alpha by 2 is pi by 2. So the formula of y coordinate of the center of mass becomes r sine pi by 2, which you know is 1, divided by pi by 2. So that is nothing but r into 1 divided by pi by 2. So again it's 2r by pi. So once you are familiar with the general formula, you don't need to separately remember the formula for the semi-arc, semicircular arc. It's just one particular case of the general formula. General formula is the one which is more useful. Okay, so, so with these couple of examples of linear distributions and the one we had done last time also, now let's move on to surface distributions.
Sir, so this is
The
general
second
formula.
category.
That
Yeah,
is
that this
my sense.
alpha 1 is the general formula. So any particular angle subtended. Okay. Okay, Aditya, I'll take you back to that just a minute. It is a special case of the general formula. Okay, the semicircular arc is a special case of the general formula. So the special case is that alpha is pi in the case of a semi-arc. Okay, very good. Yeah, so let's come up to our next kind of situation where we are going to discuss about surface distribution of mass. So in general, as we discussed, in this case, when we are doing this integration, or for the individual coordinates, whatever, dm has to be sigma dA. So this is the important thing, where sigma is mass per unit area, okay, and dA is a surface element. Okay, so let us look at an example. Now I'm going to take the example of an isosceles triangle, and although we know how to calculate the centroid of the isosceles triangle using this thing, using geometry also, but we will use integration over here. Okay, so this is an isosceles triangle shaped, okay, thin surface, okay, like a plate, like a triangular plate. Okay. So let's say these two lengths are L each, and the base is B, and the total mass is M. Okay. Now let us say L is to B is 5:6. So we have to find the position of the center of mass. So let's understand how we will do this next. So once again, we can see that because it's an isosceles triangle, okay, if we draw the bisector through the vertical angle, that will be a symmetry axis. And that will also perpendicularly bisect. So this angle, let's say theta, is equal to this angle theta. So therefore, you can always take the direction of the axis as we please. So this angle is equal to this angle. This is equal to this. Okay. So this becomes a symmetry axis. So once we know a symmetry axis, at least we know one thing, that the center of mass is lying somewhere on this axis. So where it's lying. So we are left to just finding out one thing. Integration y dm divided by the total mass. Where dm is sigma dA. Now what about sigma over here? This should be total mass divided by total area. Okay. So that is m upon area. Now let's come to how to calculate the area of this particular triangle that we have got. So you'll notice that we know the, yeah.
Sir, if we take,
Yeah, tell me, beta.
sir, if we take that x-axis on that, sir, B,
On the base,
yes,
huh.
then it is applicable.
We can take that way also. But I'm just showing you a convenient method that we take the top vertex as we can take this, this point where the base is bisected by the y-axis. We can take that as our origin and take the horizontal axis as our x-axis. That will also do. There's no problem with that. Understood ना?
Okay, sir.
ठीक है. अभी देखो L is to B रेशियो कितना था अपना? It was 5:6 ना?
Yes, sir.
Okay. So I can write this as, let's say, 5x. Okay. So then this is 6x. Okay. So this will help me figure out the geometry of this triangle. So when I drop this perpendicular, I can see that this part will be how much? This will be 3x. Okay. So I can see that this angle theta, which is equal to this angle theta, is such that cos theta is 3/5. So in this case, theta is 53 degrees. Okay, so that's going to help me. Okay, and that will also help me figure out that this height of the triangle, this will be how much? This will be 4x. This height will be 4x. So the area of the triangle, which is half into base into height, will be half into 6x into 4x. So that is 12x. So we can write that as 12/5L also. Or so 12x square. Or we can write that as 12/25 L square. Or b square by 3, whichever way we want to write it. Okay. So this area in the denominator here will become how much? It will become 12/25 L square. Oh, that's the same thing as b square by 3. So that is sigma. Okay, now next thing what I have to do is I have to select an area element. So what I will do is we will divide this into horizontal segments or horizontal strips, because the y-axis is the axis of symmetry. So what we will do is at some y coordinate like this, okay, we will cut a horizontal strip like this. Like this. Which is of very small thickness dy. Okay, so this will become our surface element, which is the length of the strip, which is 2x, into the thickness, which is dy. So that is the next thing we are going to substitute in the integration. So this thin strip its mass is going to be how much? Its mass is going to be so this thin strip, its mass is going to be sigma into its area. But what about its y coordinate? The center of mass of this thin strip is at this point only. So whatever y distance I've written from the origin of that strip, that is where the mass dm is located. That is the y coordinate of that mass dm.
Sir,
Yes.
sir, can you tell that how you calculated DA, differential area?
How we calculated dn? Let's come to that. So देखो, we have this isosceles triangle. Okay. So for this triangle now, at some distance y from the vertex, like this, I'm just cutting a strip like this. Let me. So because this strip is very thin, we can treat it like a rectangular strip. This edge thing does not matter. So if this distance is x on this side, then this is also x.
Yes.
How we know that? Because this angle is bisected by the y-axis. Okay. So now what about, and the thickness of this strip is dy, because this is our y-axis. So a differential length along the y-axis is nothing but dy. Understood now? So ये
Yes,
strip
sir.
जो है, इसका length कितना हो गया? Its length is 2x. Okay. And its thickness is dy. And it's got a bit of a corner, but we are ignoring that because the thickness is very small. So you can treat
Yes,
it
sir.
like a rod of length dy. So its area dA is becoming length into thickness. So that's 2x into dy. That's becoming this. Okay. Now the next thing you'll see is very interesting. If you look at these 2 points as, let's say, PQ, and you also think of these 2 points as RS. Okay. So now you can see that triangle PQO and triangle RSO, they are similar triangles, right? They are the same
Yes.
angles. So PQ upon height of this one is equal to RS upon Y. Height of the triangle PQ. ठीक है? Now you'll remember the triangle PQ में ये height कितना था? This length we had taken as 5x. So this was 3x.
4x.
This was, yeah, so this was 4x. Okay. So this height was 4x. This height. So 6x, which is PQ, divided by 4x, which is the height, is RS, which is 2x. Okay. You'll have to use some other symbol over here. Okay, so let's take these symbols as prime. So you're taking this as x. Divided by y. So from this I can write y, or rather I can write x as how much now? 3 by 4y. I mean, that was anyway obvious because you can see that this angle is 37 degrees now. So you can use trigonometry also. Because these two angles were 53. Okay. So you can use trigonometry also, that y upon x is equal to tan 53, or x upon y is equal to tan 37. So from that, we use this. Okay. So once you got that, we can express this area as 2 into 3 by 4 y dy, or 3 by 2 y dy. Okay. So now the mass of that strip, it was sigma into dA. So that mass will become, now sigma, remember, was how much? It was 3m by b square, where b was this base, okay, into 3 by 2 y dy. Or we could also express it as 25m by 12 L square into 3 by 2 y dy. Okay. So that is becoming my dm. So y coordinate of the center of mass is integration y dm divided by total mass. So that is integration of y into this factor. Okay. From y equal to 0 to y equal to how much? The total height, which we'll substitute later in terms of L. So you can also see that h by L is equal to sine 53. So h should be equal to 4 by 5 L. So we'll substitute that in terms of L later. So now take all the constants outside from the integration. So 25m by 12L square into 3 by 2. All this comes outside. Okay. We are left with the integration y into y. So that's y square dy integrated from y equal to 0 to y equal to capital H, which will later substitute as 4 by 5L. Okay. And this thing is divided by m. Okay. So I'm just going to minimize this a little. Make sure you understand the steps up to here, then we'll complete the integration. Okay, so let's
Sir,
come to the
can you
final
wait
step.
Sir, 1 minute,
Okay,
please.
yeah, sure. If there's any doubt in any of the steps, just let me know, including how we got sigma above, the relationship between theta and L and B and all these things.
Done, sir.
Yeah. Okay, so let's come to the final step, the integration step. So this is becoming how much now? 75. No, we can cut off the 12. So 25 by 8. Okay, L square. Now into y cube by 3, which we are integrating from y equal to 0 to y equal to h, which is 4L by 5. This will become 25 by 8L square into 1 by 3 into 4L by 5 whole cube. So 25 by 8 into 3 into 125 to 64 into L, because L cube and L square in the denominator will cancel. So 725, it's a 64. So 8 by 15L, that is what I am getting as the y coordinate of the center of mass. And interpretation wise, what this means now is that for this particular type of triangle, where these two angles were 53 degrees, my center of mass should lie on the angular bisector or the symmetry line from this point vertex O to the center of mass, such that this distance OC should be equal to 8L by 15. Okay. Okay, so hope this is clear, people. Now, before going into another problem, I'd like to show you an interesting application of calculus in general other than this. Okay, so next example is not related to center of mass, but it is just a general application that proves that area of a triangle is equal to half base into height by integration. Or how do we derive this formula by integration? Let's see that. Okay. So this time, let me consider an absolutely scalene kind of triangle. Okay. Which has sides, let's say A, B, and C, or let's take the base as B. Okay. A not equal to B not equal to C in general. Okay, but let's also see that if I drop this perpendicular here, this height is h. So this particular height is h. So now what we will do to find the area of this triangle is that we will cut a horizontal strip. Okay. Again, such that the thickness of this strip is dy, and this length from here to here is y, whereas this length from here to here is x. Okay. So again, if I have considered this triangle to be OPQ and this triangle to be, let's say, S. Okay, you see that triangle OPQ and ORS, they are similar triangles. Okay, so x upon y, that is base upon perpendicular or base upon height, should be equal to b upon h. So I can take x as y into b by h. That is my first step. Okay. And as we saw earlier, the area of this strip that is length into thickness. So this time I've taken the full length as x only, is this. Okay. So the total area should be the integrated area of all the strips. So it should be x dy integrated from y equal to 0 to y equal to h. This is my second equation. So hope this is clear to all of you, this calculation that we are doing. Okay, so this is that h, the total height. Okay. So now just substitute this over here. So substitute this in this equation. So this becomes integration of y into b by h dy integrated from y equal to 0 to y equal to h. So d by h comes outside, y dy integrated from 0 to h. So half base into height. Okay. So this is, we are applying the same kind of principle we did earlier for the center of mass position, but to derive something much more basic and fundamental, that is just to prove that the area of a triangle is indeed given by the formula half base into height.
Sir,
Yes.
so same method can also be used to find the area of a circle.
Yes, exactly. In fact, in the next derivation when we do, I'm going to show you that we can prove that area of a circle is pi r square, or area of a disk, surface area of a disk is pi r square, by using integration. but there we will slice the disk into rings. Here we have sliced the triangle into horizontal strips. There we can slice it into horizontal strips also, but it will be more convenient to slice it into thin rings, concentric rings.
So as to
Like
make a
when you have a
calculation more
sliced piece of,
simpler,
sorry, come again, Beta.
sir, so as to make our calculation more easy.
Yeah, actually, to make the calculation more easy, we can take horizontal strips also for the circular thing. But if we take circular rings, thin circular rings, one on top of the other, concentrically lined, like the layers of an onion. Like if you slice an onion into a disc, now that disc-shaped slice of onion, further you can see, has concentric layers. So if we take that kind of symmetry, it's even easier to set up the integration compared to slicing it into horizontal strips. So these are some of the important techniques of using integration, as I was telling you. So this chapter is very important from that point of view. This part of the chapter, calculation of center of mass, in learning the types of uh, techniques and methods that we can apply in integration. Okay, so hope this is clear to all of you people.
Yes, sir.
Okay, so with this we'll conclude today's lecture. Next lecture we'll continue with more examples of integration, moving into volume distribution also, where we'll use dm is equal to density into dv or rho dv, that type of application. Okay, and once we are done
Okay,
with
sir.
that, then we will come to the next part of the chapter, which is about motion of center of mass and linear momentum and things like that. Okay, so that's it for today's session, people. All the best and thanks for attending.
Thank you, sir. Bye, sir.
Bye. Bye.